So lesson 5.7 is all about bringing systems back into the conversation and combining the concept of solving a system with the fact that we're going to be working with linear inequalities. So in the last lesson, we explored this just by itself, just linear inequalities in two variables when there was just one inequality. And now we're going to kind of bring that into the whole concept of solving a system. So just like we talked about before, the solution to a system is going to be any values that make both inequalities true, right? It used to be for equations, but now we're looking at values that make both inequalities true, that hold true for both. And so in the first few problems, that's what we're testing for. Very similar to what we did with equations. We want to test the point to find out if it is a solution to the system of inequalities. Well, it's only going to be a solution to the system of inequalities is if it makes both inequalities in the system true. Okay, so we're going to go through these probably pretty fast because this is really similar to what you have done before. So if we wanted to test whether this origin point is a solution, we would insert it here, find out if it makes the first equation true, and then insert it into the next one and check also. It's only going to work or be a solution, sorry, if it works in both, right? So I'm going to set up my little organizational tool here and test each one. So the first inequality is where y is greater than 2. So if I insert this, I only need to use the y coordinate. The question is, if I plug in a 0 here, is 0 greater than 2? Right? Is that a true statement when I plug that in? And the answer there is no. This does not work in that first inequality. Well, if it fails the first one, I don't even have to bother with the next one. It already failed the whole concept of it being the solution to the system. Because for it to be that, it would have to be true in both. So the answer for this one is no, since it did not work in one of the inequalities. Okay, let's try for number 2. So on number 2, I have a system of inequalities here, and we're testing -1, 1. So, same thing. I will test it in each one, see if it works. So if I make my little organizational tool here, the first inequality is all the y's that are less than 3. So I'll use just the y coordinate for this one and say, okay, if I use 1 as my y coordinate, does it make this true? Is 1 less than 3? Well, the answer to that is yes, it is. So it passes the first one, and that's phenomenal news, right? But we still have to check to see if it works in the second one. So in the second inequality, it is all the y's that are greater than x minus 4. So when we insert this ordered pair, y is a positive 1, x is a negative 1. And so I'm putting this in here and this in there. And then I'll simplify this side. -1 and -4 is a -5. And then I check to see if this is true. Is +1 greater than -5? And the answer to that is also yes, right? So it passes both inequalities, and then we can conclude, yes, this is a solution to the inequality system. So pretty straightforward there. A lot of that is review. The only difference is we are reading that final statement with an inequality symbol instead of an equation. Okay, let's try one more on number 4. Maybe press pause, try it on your own, and then you can press play again and check your work. So we are testing this x and y. The first inequality was y's that are less than or equal to -x plus 4. When we insert this, that's going to translate to 4 is less than or equal to a negative, and then I'm plugging in a 0. And -0 is still just 0. So I just is less than or equal to 4. Is that true? Well, yeah, it's equal, right? So it meets one of those two criteria. It either needs to be less than 4 or it needs to be equal to 4, and it is. So that works. And then we'll test it in the next inequality. And we'll insert our point. So y would be 4 here, and x would be 0. 5 times 0 is still 0, and 0 minus 3 is a negative 3. So is 4 greater than or equal to negative 3? Yeah, it's greater than, right? It meets that top criteria, so it works in that one as well. And then we can conclude that, yes, this point is a solution to the inequality. Okay, so that's testing the point. Now, what's different, and this is a really fundamental difference, so if you get anything out of this lesson, this is it, right? For our systems of equations, right, our solution was where the lines intersected, and it was at a single point. So if I graphed, just as a quick review, one line and I graphed another line, I had one single ordered pair solution, which was where those lines intersected. That is no longer the case when it comes to inequalities, okay? Just like when we were graphing inequalities yesterday, our solution was an entire region or half plane. The solution today will be where those regions or half planes intersect. And so our solution is still going to be an entire region of a graph. It's just a region that makes both of the inequalities true. So you're going to essentially do what you did in that last lesson and graph one inequality, then you're going to graph the other linear inequality, and you're going to look to see where those solution regions overlap, and that's where your solutions for both are going to live. Okay, but that means that these systems have much more than just one solution. It's no longer about the intersection of the two lines. It's about the intersection of the shaded planes or the shaded regions. Okay, so let's see what that looks like. Let's try number 5. We have a system of linear inequalities, and we want to graph it to find those solutions. So that just means we're going to graph both of them on the same graph and then look to see where they intersect. And I'm going to give you some tips and pointers to kind of keep track of this. Let's start with this one. Y is greater than negative 2. So again, just like yesterday, first of all, when we first do this, we're going to graph that related line. So in this case, it would be the y equals negative 2 line. That's going to create the boundary line for this particular inequality. So if I think about what kind of line y equals negative 2, hopefully we all feel really comfortable that that is a horizontal line at negative 2. Okay, and so that's, right now I'm just focused on the line itself, and I'm treating this as if it were an equation just temporarily. And for this one, guys, it's just all the y's greater than this line, so I'm going to go ahead and make sure that I make this a broken line. Okay, so that's my boundary. And then we really are not just interested in points on the line. In fact, we don't even want points on the line. That's why this is broken. It's like an open circle, right? We just want everything greater than this line, greater or above it. So again, this part would be what's greater than. And so this entire, if I was just graphing this inequality by itself, this whole region would be the solution. And I want y'all to notice I'm keeping this pretty light because this is not my final answer, and I don't want this to get really messy. So I'm going to just kind of lightly shade this in to kind of keep track of where it is, but I don't want to go super heavy because it's not where my final solution is. Okay, but that is a solution to the first inequality. Okay, now let's graph the second one. For this inequality, we're first going to graph the boundary line where y is equal to 3x. Okay, so we'll do that first. And this one does have the bar, so we'll make it a solid line. Okay, so let's see. Y equals 3x means I have a y-intercept of 0. Since I don't have a b, I just like saying plus 0 here. So I've got a y-intercept of 0 and a slope of 3, or in other words, 3 over 1. Okay, or down 3 and back 1. Okay, and this is going to be a solid line because it can be equal to this boundary. We do want solutions that are equal to it. So it's almost like doing two different problems, but you're doing them on the same graph. So there's my boundary line, and my solution set did include the boundary, so I made it solid. But I want everything that is less than this boundary line. So I got to decide, okay, where are my points that would be less than this boundary line? Would they be in this direction, or would they be in that direction, right? So I can see here that toward the right is going downward away from this line. This is my less than. That's also on the y-axis. This is the side that has the values that are less than my y-intercept. So for this one, if I were graphing it by itself, this would be the solution region for it. Okay, everything here. Where now that I have them both graphed, the solution to the entire system, guys, is going to be where these two shaded regions overlapped, right? So for the pink line here, it was everything greater than this line. And for the blue line, it was everything less than or equal to that line. And the overlap is happening in this section. And that's where I'm going to get more serious about my shading, to show that final solution space is where the shading overlaps. This is the region that makes both of these true. Okay, any point I pick here is going to be greater than this pick line and less than or equal to that blue line. So it meets all the criteria. That's my solution space right there. And that's really what you're doing today. This is how you solve a system of linear inequalities. And then you can pick any point in that region. You could test it like we did up here. That's what you would be doing if you were testing any point to make sure that your answer is correct. Okay, let's flip it over and let's try. Let's try number 7 here. Okay, so on number 7, this is our system of inequalities. And first we're going to graph the boundary line. So we're going to treat this like a linear equation for just a moment. And then we'll figure out our shading. So for this one, for a moment, I'm just going to graph the line to create my boundary here. I'm just going to graph y equals x minus 2. And I notice that it's got the bar. So I'm going to go ahead and make that a solid line. Okay. So that has a y-intercept at -2 and a slope of +1. Up 1 over 1, up 1 over 1, up 1 over 1, right? So it generates several points. And we agreed on a solid line. So that's what I'm going to do. Solid line. That's the boundary, and it's actually part of my solution set. I am allowed to have points on this line as the solutions. But I also want anything greater than this line. So if it helps, put your pen or pencil down and figure out, okay, which half plane would be above or greater than? Would it be in this direction or would it be in that direction, right? So hopefully you agree this is the part that's above this boundary. So this would be the solution to this first one. And I'm going to keep it fairly light. It's really there just to kind of remind me. And then I'm going to go for the next one. So for the next one, I'm going to first graph the boundary line y equals -x plus 2. This one does not have the bar, so I'm going to keep this a broken line when I make it. But it has a y-intercept at 2 and a slope of -1. So that means that my line should be falling. So -1 over 1 is just down 1, forward 1. Down 1, forward 1. Down 1, forward 1. And I know that we're seeing our lines intersect there, but that's no longer opposite in actually. In fact, since this line, boundary line, is not part of my solution set, that intersection point wouldn't even work if you tested it, okay? So in inequalities, that is not our goal. So we're going to make this broken line here. And there's my other boundary, and I want everything less than this line. So think about where those points would be. These would be greater than because they're above, and then these points would be less than, they're below. So the solution to the second inequality would be everything in this region. And once I've done both solution sets, I can hone in and realize that it's really this corner here to the right that holds the solutions that are true for both. And so that's when I kind of formalize and get serious and commit to my shading here, because that's where my solutions live. So I should be able to pick any point in that region and plug it in, and it should then make both of them true. Any point in this section is either greater than or equal to the pink line and less than the blue line. So that's the big idea. Okay, that's solving systems of inequality. So press pause, try number 8, try it on your own, and then test it and check it out. Okay, so hopefully your system of inequalities looks like this when you graphed it. The top one, when I rewrote it as solving for y, I got y's that are less than negative 2/3 x plus 2 when you solve for y there. And for this bottom one, all you have to do is move the 1 over, and you get y is greater than or equal to the negative 2x plus the 1. So this is your top dashed line, and you wanted everything less than it, so there it goes down. And then for this guy, there is the blue one. It's a solid line there with a negative slope, and we wanted everything greater than or equal to it. And if I then check it out to finalize this, I realize that my solution, where these shading regions overlap, is this wedge sort of the right, to the bottom right. I think I said right over here. That's left. I might have said that earlier and I realized that. I know my right and left. I don't know what I was thinking. Okay. And that's the final solution. So hopefully this is feeling pretty good. You will see problems both ways, where they have light, and dark, and then sometimes they present problems on the EOC or on the textbook that just have the final solution shaded. So you want to be comfortable with both options. Okay. All right. On these, again, similar like the previous lesson, they've given you the graph and the final system solution, and you want to work backwards to write the system. So let's practice a couple of these. And then we'll go on to the next type of problem. So if we wanted to work in reverse here and create the system of inequalities for which this is the solution, I basically would want to just figure out each individual boundary line and shaded inequality and then just put them next to each other. That's really it. Okay, so I could start with this line right here. With right away I can tell it's a vertical line, and I know that vertical lines are always an x equals a number. So it would be x equals, and then it looks like my intercept is at 2. And then really the only difference is instead of saying x is equal to 2, I'm going to find my inequality symbol. Well, this is dashed, so it does not have the little or equal to bar. And they're shaded to the left, which are the x values that are less than 2 on the number line. So my symbol here that matches this graph would be all the x's that are less than 2. So that would be the inequality for this particular inequality right here, this vertical boundary line and being shaded to the left. This is a horizontal line, so right away I know that's the kind of line that I write as y equals a number, and it's at 3, so I know that it's going to be, it normally would be y equals 3, except instead of an equal sign, I'm going to decide what inequality symbol works here. Well, they shaded everything below it, so that is less than. And it's a little hard to tell, but that is a broken line, so I don't want the bar. So these are the two inequalities that were graphed, and then I can just finalize my answer and say, okay, well then basically this is the system that we're looking at right in front of us on this graph. That's a system that's showing the solution to, this is a graph that's showing the solution to this system right here, okay? These are both horizontal lines, so let's try that. And it looks like the darkest part is in the middle, so it's everything in between. Let's write this inequality here. This has a intercept at 3 again, and it looks like it's a solid line, and the solution's below it, so it must have been less than or equal to the 3. And this is another horizontal line, and it is all the y's that are greater than, because it's dashed and it's shaded, the solution's above us, and it looks like 1 is the intercept there. So that would be the system that produced this graph. The system with the boundary line at y equals 3 and everything less than or equal to included, and everything that is greater than 1. Okay, so maybe try this one, give it a pause, and then try it out. And if you did that, so this one, I'm going to start with the solid one here. It doesn't really matter which one you put first. But this solid line, I can see it's solid and shaded above, so I know it's going to be greater than or equal to. And then it looks like it has the slope of 1, because it's up 1 over 1, up 1 over 1, up 1 over 1. So it's a slope of 1, or 1x here. And a y-intercept at 1. So that would be one of the inequalities, the solid line here. The other inequality is this line, so let's talk about that one. That one is broken and shaded below. So that would be just everything less than. The slope is -1, down 1 over 1, down 1 over 1. down 1 over 1, and so forth. So a negative 1x, or just negative x, however you want to write that. And then the y-intercept is also 1. So there's your system. Okay, so that's just working in reverse, is setting that up from the graph. Okay, all right, so if we feel pretty good with that, then let's talk about how we actually set these up from word problems and find solutions, right? So let's talk about number 13. Wording, the vocabulary here really matters, so be careful with the vocabulary, especially when trying to set up what an inequality would be. So number 13 says you can spend at most, so right away at most means you can spend less than or equal to that value, right? So if you can spend at most 60, it means that is the most. You don't want to spend a penny over. So even though the word most is there, we talked about this back when we did inequalities, even though the word most is there, this actually means a less than or equal to sign. Okay, so you can spend at most $60 means that what we're going to spend needs to stay less than or equal to 60. Okay, so you can spend at most $60 on beads. A bag that contains red beads costs $2 per bag. So maybe I'll call that X and say, okay, it's $2 per bag, X being the number of the number of bags. Okay. A bag containing blue beads costs $3 a bag. So maybe I'll call those the Y, the number of bags of blue beads, and those are $3. Okay. You need more bags of blue beads than bags of red. So however many bags of blue beads, which we just agreed to make Y, we need more of these than of red. So however many bags you get, which is Y, of blue beads, it has to be greater than the number of red bead bags. Red bead bags, that's a lot to say. Okay, so basically Y has to be greater than X. Since we assigned the Y to blue bead, the number of bags of those has to be more than the number of bags of red. That's what that says. So it actually helped us set up one of our inequalities in our system. So if we write a system of linear inequalities, well, one thing we know is that the number of blue bead bags has to be more than the number of red bead bags. So there's that, which we just came up with here from that last sentence. And then the other one is about money. So money, 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 right? How much these cost? We know it's $2 per bag of red beads and $3 for the blue. That has to be what? At most, less than or equal to $60. Okay. So there is our system. That's our system of inequalities for the scenario. We know that whatever this total cost is, it's got to be at most 60, and we know that we need more blue than red. Okay? All right, so that's our system. Then we graph the system of inequalities in part A. So let's come here to our graph. We decided X was going to be the number of red. So this is number of red bead bags, and this is going to be number of blue bead bags. Okay, and then we can graph these two lines. Well, one of those lines is just the Y equals X line when I go to graph the boundary itself, right? So Y equals X, well, that's pretty easy. It's got a y-intercept of 0 and a slope of 1. So it comes up like this, and it just keeps going that way, right? And they said you need more, not greater than or equal to, just greater than. So it's going to be a dashed line. So a dashed line all the way up. And now for the shading, I want everything greater than this line, so I'm going to keep it pretty light, but I know that this region would hold all of the values where Y is greater than X, right in there. Okay. All right, now let's graph this guy. It's in standard form. I'm a fan of intercepts, right, with this. Y'all know this. Let me see if I can actually do intercepts with this guy. So if I did, my y-intercept would be 20, so at least that's a good start. 60 divided by 3. And then my x-intercept would be 30. That falls off my graph, so no luck there. Okay, that's all right. I can just rewrite this if I need to, and that's perfectly fine. I'm gonna just rewrite it so I can use slope. So if I move the x term, I get that, and then I divide everything by 3. So divide, divide, divide. I'm kind of running out of room here, but divide everything by 3, and I get y's that are less than or equal to that negative 2/3 x plus the 20. So this really just helps me reveal that slope. So from that y-intercept of 20, I'm going to go down 2 and over 3, down 2 and over 3. I'll do it a few more times. And it can be, when I spend at most 60, that means if I walked out there with $60 exactly, I would be okay, but not anything greater than that, right? So it can be a solid line, it is including, but I do want to stay either at that line or below it. So that's this region in here. And of course, the solution to the entire thing is where those overlap, which we can start to see is right in this section. So I'm gonna not get crazy, but definitely make this darker so that I can make it really clear to my reader that this is where my solution options live, okay? And that would be your graph. And then it says identify and interpret a solution to the system. So I could pick a point here. Any point that lands in here would be fine. So maybe I'll go over 3 and who knows, up to 10, something like that. That would be a point. It definitely falls in my region. Okay. And so identify and interpret a solution. So one possible solution I just picked is 310. More importantly, let's interpret that. Well, what does that mean? Well, X was the number of red beads, and the Y is a number of blue. So this basically means that you can buy 3 bags of red beads and 10 bags of blue beads. Okay, and you would have more blue than red, and if you plug it in here, it should definitely keep your budget under 60 bucks. Okay. All right, let's take the next one. So use the graph to determine whether you can buy 9 bags of red beads and 12 bags of blue. So all I have to do is find that ordered pair and see if it lands in my final solution region. So can we buy 9 bags of red? So let's go over to that. So here's 9 and 12 bags of blue. So if I go up to 12, that would be right here. This is where that point is. Is it in my solution set? Well, yeah, it is. Okay. So the answer is yes. Okay. It is in the overlapping shaded region. Shaded region. Okay. All right. So then we would be able to tell if that point is a solution. Okay. So that's the big idea. We're going to skip number 14. I think I will want to do that one in class together tomorrow, but for now, and let's go ahead and flip it over to the second set of notes, which is really just practicing word problems. So we'll do 1 or 2 of these, and then we can do a couple others in class, and we'll call it a day here on the homework. So let's go ahead and try number 1 here. So if it says here, Julia is going to the store to buy candles. Small candles are $2, large candles are $5. She needs to buy more than 20 candles, but she cannot spend more than 70. Okay, so we've got some information about just quantity. We're going to buy some small, some large, so that can be our X and our Y. but we need to buy more than 20, so that's one total, and we should be able to set up one inequality based on just number of candles. And then the other inequality or limitation is about how much money, right, we can spend. So that's where that $5 and $2 are going to come in. Okay, so first, write a system of inequalities that expresses Julia's situation. Use X to represent the number of small candles. Y can represent the number of large candles. Graph the inequalities in the region, and shade the intersection. Okay, so let's first set up the system here. So let's talk about quantity first. X is going to be the number of small candles. Y is going to be the number of large candles, but we know that all together she needs to buy more than 20. So whatever this grand total is as far as quantity, we need it to be more than 20. Okay, so there's one inequality. The other limitation is, of course, cost. Sure, she wants more than 20, but they're not free, right? So every small candle she buys is $2. So we have to multiply that quantity times 2. Every large candle she buys is going to cost her $5. And she can spend no more than 70. That means that her expenditure needs to be less than or exactly 70, but no more than 70, not a penny more. So there's the second inequality in our system. Okay, all right, so then let's go ahead and graph this. Let's find out how many squares we have here. Looks like 20. Okay, so this is up 20 by 20. That's always helpful to figure out how you're going to space this out. This guy has intercepts at 20 and 20, right? So 20 divided by 1, 20 divided by 1. So I know that line can fit. And then this one, I think they can both fit just fine if we go by ones. So 0 to 20 going by ones. I'll label the other stuff in a second. X was the number of small candles. And this is the number of large. Okay. And let's go ahead and graph this. So we have our system set up, and now let's graph it. Well, this one, like I said, is pretty nice with the intercepts. So it's got an x-intercept at 20 and a y-intercept at 20. So we're going to put the y and the x-intercepts there. And it's going to be a broken line. Maybe I'll go back to colors on this one just to make it easier to see. A lot of people use colors sometimes to do these systems of inequalities. Okay. So, and we want everything greater than this line, right? It makes sense. She wants more than. You can always test a point. Like if I bought one of each, right? We know that wouldn't work. It's not more than. So it definitely needs to be the other region, which is the region above this boundary line. Up there. Okay. We're going to pin on that. And let's do this guy. Let's do these intercepts. So the x-intercept is 35. That's way too far out. The y-intercept is 14. I can do that. Okay, so let's go 1, 2, 3, 4, 5, 6, 8, 9, 10. There's 14. Definitely have a y-intercept there. And then I can maybe use slope. So let's actually solve this for y. If we move the 2x to the other side, we get 5y is less than or equal. We got this guy plus 70. And then we divide everything by 5. So y is less than or equal to negative 2/5 x plus the 14. We already had that 14 marked, but this is the slope we're going to use. And this line is going to be a solid line. So once we go down and then over 1, 2, 3, 5, down to, we can make this a solid line. Because it's okay if they spend exactly $70. It just can't be a penny more. So there's our boundary. Okay. And we want to stay less than or equal to that. So we're going to shade below it. And of course, we want to meet both criteria, right? We want to make both people happy, both equations, inequalities happy here. So the region that is going to work here is going to be this little wedge right in here. That's where our solutions are really going to be. That is where I would get more than 20 candles, but I would stay within budget below 70 or exactly at $70. So it's this region right here. So use the graph to determine how many large candles she can buy if she buys 14 small. So let's find 14 small and find out what our options are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14. So if I go up, I can't be on the line, but I could have this many right here or that many right there. So if I figure, say I should have labeled my axes. Let's find out what those are. Where am I at? 1, 2, 3, 5, 6, 7, 8, 9. Okay. So if we do that, so it looks like 7 or 8 would work, right? So she could do 7 or 8. So she can buy 7 or 8 large candles if she plans to buy 14 small. She can buy large candles. There it is. Okay. And we're just using that region to guide whether, you know, what we can afford or what we can do here. There it is. So those are your two options, it seems like. All right. So try, let's see which else one do we want to try, and then y'all can check your work, and then we'll call it a day after that. Is there one specifically I want us to do? You know what? Let's try number... Well, I guess let's just go ahead and try number 4. So try number 4. Let's flip this over and press pause. Try it on your own, and then you can check your answers. All right, so check your answer here. This should have been the system that you should have come up with as far as what Dominic is going to spend and what the minimum number of packages of hot dogs that Dominic wants to get. So we want to spend less than the $60, so that's below the blue line I have here, but we want at least 4, you know, of the hot dog packages. So the number of hot dogs, this is at 4. Needs to be at or greater. So really our final solution region is this triangle down here. That's where my final solutions are at, right? And then if he wants to buy 7 packages of hot dogs, what is the max? So 4, 5, 6, 7. We want to know what is the most number that he can buy, when he can buy up to 4 wings, and you can always test that, right? So if we go to hot dogs are 7 and we see what is the most we can still afford and stay within budget, and it's kind of close to that line. So it's, if you need to test it in the equation, right? We're thinking it's 4, so we would be buying 7 packages of hot dogs, and we are going to test to see if 4 still keep us under $60 there. Kind of ran out of space. Well, this is 35 plus 24, and 35 plus 24 is 59. So yeah, he would be able to do that with $1 to spare. How cool is that? So you can always check it to be sure. We might do a few more of these, but we'll do them in class, so no worries on that on the homework.